Hey guys, welcome back to my YouTube channel. So in this lecture, we are going to see about another one fundamental gate, that is NOT gate. So NOT gate is also considered as an inverting gate. So what are the input that you are giving, that will be reverted at output. So it will be considered as A naught. The diagrammatic representation will be the single input output with a bubble in that. So if the bubble is there, then the input A will be complicated or toggled to of opposite sign. So let me draw a truth table for this one. So if we take input that is 0 and 1, the output will be opposite, that is 1 and 0. Okay. So that is what the difference of this thing. So let me draw a diagram to mention this one. So this can be represented in transistor logic because that will be quite able to understand easily. So this is the transistor, that is NPN transistor. So here we are giving A as an input to this one, and that is directly connected to ground. So this is some simple representation that we are taking. So this is R, which is connected to VC, which is plus VC. I'm removing that short circuit, so which is connected to plus VCC. Okay, so here we are taking the output, that is Y, so which is equal to A bar. So here the condition is that A, the transistor, Q, which is B, the transistor, and here the output Y. So when input is A, input is 0, then the transistor will be in off condition because there is no net current flow. The transistor will be in off condition. So if the transistor is in off condition, this one directly connect to output, so then output will be 1. So if transistor is 1, then this will be connected to ground. So this is not taken into account. So the Q will be on and this will be equal to 0. Okay. So I hope you guys able to understand the NOT gate logic. So it is quite simple, like how we are done for the OR gate and AND gate and the OR gate. So this is how all the logic gates, like even if you guys may represent a high level logical diagram outside, but the internal structure will be like this one, maybe transistor or maybe diode or any kind of things it will be. So from this, we are concluding all our understanding on the basic logic gates. So now let's get into jump on universal logic gates. So universal gates. So universal gates is the concept where what will happen is that any kind of basic logic can be derived from obtained from this logic. So logic gate is said to be universal if we are able to implement any logic. So if we can able to implement any logic. So implement any logic using only one type of gate. Using any one of one type, so maybe any one of the universal or special type of logic gate, then we call that as a universal gate. So we will be seeing in this further lecture. For an example, if we are able to implement AND, OR and NOT using only one type of gate, then we can say that as a universal gate. So here let's see some kind of universal gate that are. So first thing is the NAND gate. So NAND is one of the universal gate. So we will be proving that how we can call the NAND gate as a universal gate. So the NAND gate structure will be like this. So AND with a bubble. So this is what the NAND gate. So if A, B is there. So AB is product and we are taking the complement. So according to De Morgan's law, if the complement we take A bar plus B bar. So I think this is you able to understand the dot will become as plus because like similar to the complement. So will be dot will become as plus. So this De Morgan's law, I think everybody knows it. Even if not, please make a note of it. So let's drive the truth table for the NAND gate. Okay. So let's take the input A and B, product of AB and the complement. So 0 0 0 1 1 0 1 1. This is as simple as AND gate logic. If you have to take the complement of that, so this is quite inverse of that one. So here also same thing. The commutative rule will follow because A B bar which will be equal to B A bar. So commutative will follow, but the associative will not be followed in the special case or universal gate and not associative. So this is one very important thing. So associative is not follow. So this is not associative. Okay, so this is understood, I think. So let's see the another one of the universal logic gate, that is NAND. The other one is NOR. So we will be proving that how other logics can be driven from here. First, let me explain what all the possible gates that are available. So here the same thing like OR gate with an bubble. Okay, so A, B, so it will be equal to A plus B the whole bar, which will be called as A bar, B bar. Okay, so this is also same like De Morgan. So here also same thing, commutative will be followed, but associative will not be followed here. So let me draw a truth table directly. So A, B, and output A plus B the whole bar, 0, 0, 0, 1, 1, 0, 1, 1. So if we add and take the toggle, then it will be 1, 0, 0, 0. Okay, so this is how the NOR gate will be work. So this is the basic functionality of NOR gate. So now let's see how we can call the NAND gate and NOR gate as a universal gate. So we are going to prove that how we can call NAND gate as universal gate. NAND as universal gate. So first let's try to implement NOT. So NOT is that we have to take a complement of the things. So this is very simple. So we could take a, this is NAND gate, right? So let's couple both the input. So A bar A, which is A, which is bar. So this is NAND gate, simple. Or we can try another one like as a floating input that we already suggested. So just to connect this to VCC. This is R and this is A. So if it is open, then this is also A bar. Okay. So simple. So this is how we will be doing that. So NAND can able to do the NOT function. So which will be inverting the thing. The concept is that using the NAND gate, we have to implement this logic. NOT gate logic is implemented. So A is given, A not is get. So next AND gate. AND gate output. So you have to prove that A, B, we have to get it. So from this, let's take the understanding of how things will work. So let's get a 2 input NAND gate. So if we apply A, B here, so we will be getting A bar, A, B whole bar. So if we give this to again the entire toggle, then we will be able to get AB. So, okay, so this is similar to this one. So we are able to get the AB AND function with the help of 2 NOT gate. So here number of gate required is 1. Here number of gate occurs 2. So 2 NAND gate is to get the AND behavior. So here the OR. So OR is A plus B, right? So how we can get the A plus B is that. So let's take a, using the De Morgan's principle, let's take a double bar. If we take a double bar, it will be cancelled, then no issues. So if we take a De Morgan law for inner bar, then we will get A bar plus B bar, B whole bar. If we again take the bar, that will be A plus B. So okay, so this is what the quiet thing that we will be getting here. So if we take that bar twice, then the output will be similar to this one. So we can implement this logic. So first let's get able to get the A bar, B bar, and then let's multiply and take a whole bar. So let's use a single input NAND gate. So 2 single input NAND gate. So this is A, this is B. So A, B which is connected. So here we will get A bar, here we will get B bar. So if we connect both the thing to 2 input NAND gate, then we get A bar, B bar, B whole bar. So if we take that one, so A plus B. So we were able to get the OR function with the help of 3 logic gates. So here you see, with the help of NAND gate, we able to implement the NOT gate, we able to get the AND gate, we able to implement OR gate. So this is why we call them as a universal logic gate. So in the second scenario, let's take OR gate as universal. Okay. So first take NOT and NAND. So try to do similarly as like what we have done previously. So I'm giving this up to you. So here we can reverse it. Let me use AND gate first and then AND gate. So OR gate here and AND gate. So please pause the video and try to answer yourself. So here the logic that we need is the y need to be A bar. Okay. So here also same thing that we are coupling the input and taking the thing. So A. So here if you see A plus A the whole bar. So if you do it, we will get A plus A is A and A bar. Okay. So with 1 8, we are able to get the NOT functionality. Here y need to be equal to A plus B. So if we take 2 bar, then that will be very simple. So first let's take a normal thing. So A, B. So here we'll be able to get A plus B the whole bar. So if we again toggle this one. So if we toggle this one, then we will be able to get A plus B bar bar, which is equal to Y. So this is equal to A plus B. Okay. So here with the help of 2 gate, we are able to get the OR function. So in AND functionality, A bar, right? So if we take the De Morgan's law, then we'll get A bar plus B bar the whole bar. So here let's take a 2 individual OR gate functionality to get the complement of each inputs. So here it's connected to A, it's connected to B. So A, here connected to B. So here we get A bar, here we're getting A B bar. So when we connect this to an OR gate, so then we will be able to get the A bar plus B bar the whole bar. So this is equivalent of that. So we will be able to get the same thing like this one. So if we bring this bar inside, then that will be AB. So here with the help of 3 gate, we are able to implement the AND gate. So this is how we will be calling NAND and NOR gate as a universal gate. So only these two are the universal gate, you may ask me. But there is 2 more gate that will also be called as a universal gate. So one is implication. But this is not quite used in any of the cases. This is just for your understanding. So don't confuse this one with it. So implication. So implication is a thing where the output will be A plus B. So this is how the output logic gate will be looks like. So the truth structure diagram will be like this. So with the implication also, we can able to implement any logic. So this is not needed. You guys can please make a note of it. So this is the implication is one type of thing. So here also, which is not commutative. Here it is not even commutative. Not even commutative, not associative. Both things are not possible here. So this is very important thing. So there is another one thing, that is inhibition. So these gates you guys may not be seeing in your syllabus, but just to try to make a note of it. So here the y will be equal to A dot B. Okay. So here how the structure it will how look like. So here is a bar. So A, B bar. So A and B. Here also it is not commutative. So this also it's not commutative. So even if it is not commutative, then it will not be associative also. So please take note of it. These 2 gates is also universal gate. So this is also universal gate. So this is also universal gate. Okay. So if you guys need to work on it, so please try to implement AND OR and NOT gauging with using this. So this is how the universal gate. There is a majorly 2 only, NAND and NOR. So even implication and inhibition will also be some things, but that may not be used in many of the user cases. So in the next class, we will be seeing about special function gates. So which is XR and XNOR. So which is one of the very important function that this will be used in plenty of cases, like whatever the modern mathematics or modern circuit that we design, that is majorly with XR and XNOR. So from next class, we will be discussing on the XNOR and XR. So please like, share and subscribe. So stay tuned guys. So I will be seeing you in next lecture. Thank you.